continuing on with Unit 7. This is the second video for Learning Target 7a, which is all about properties of exponents. So in the first part of this, or in the prior video, we talked about the first three properties of exponents. The fact that a to the 0 power equals 1. If I have a negative exponent, I can flip that to the denominator and make it a positive exponent. So a to the negative n equals 1 over a to the n. And we talked about why we can do these as well in that prior video. Then our third property that we've learned so far is that if I have the same base and I'm multiplying the same base, I can add the exponents. So a to the m times a to the n would be equal to a to the m plus n. And this only works because remember these bases are the same. So the prior video, we talked about those three, we talked about why that's true, and we also did a bunch of examples with them. Let's move on to our fourth rule, our fourth property of exponents. Now, the prior three might get used in this video as we go through, so make sure you have those first three down first. So our fourth property says what happens when I raise a power to a power. So let's let a be a non-zero number and m and n are rational numbers. So if I have a to the m and then I raise the entire thing to the nth power, then what I would do would be multiplying the two powers together. So that would be equal to a to the m times n. You're probably wondering why. So it's important to know the why and understand that so that you can see this in a bigger context versus just trying to memorize a set of rules. So let's work through this with an example. I have x to the fifth all to the second. Well, we know what the second power means is that I rewrite my base that many times. So because my outside exponent here is to the second, it would mean that I would rewrite x to the fifth twice, and I would have x to the fifth times x to the fifth. Well, we know from our property number 3 over here that if I'm multiplying bases that are the same, I add their exponents. So because I have the same base here of x and x, I would add the exponents. So I'd get x to the 5 plus 5, which would give me x to the 10th. But another way to think about how I got the number 10 is if I go back to the original problem, I have a 5 and a 2. Well, if I multiply 5 times 2, that will give me 10 as well. And that's kind of a shortcut rule so that if I have a power to a power, I would then multiply those exponents. Okay, let's do a couple examples to solidify this. So in part A, it says x to the second all to the third. So the entire x to the second is being cubed. So what I can do is multiply the 2 times the 3. So I'll get x to the 2 times 3, which would give me x to the 6. In example B, we have a little added part of a coefficient in front, but pay attention to the parentheses. So this says 3 times x to the negative 4th to the 7th power. So when I look at this, only the x to the negative 4th is being raised to the 7th power. So the 3 is never going to change because the only exponent on it is that exponent of 1. But x to the negative 4th to the 7th will be the same thing as x to the negative 28 because I can multiply the negative 4 and the 7. Now I have to keep going with this because if I look back at my instructions, it said to simplify, which we've done, but it says to simplify without any negative exponents. So this is where that second property from our last video is going to come into play. To simplify something with a negative exponent, I can go ahead and flip that part down to the denominator. So the 3, remember, doesn't have a negative exponent, so the 3 will stay in our numerator, but I can rewrite the x as x to the positive 28 down in the denominator. And let's look at our third example here. So it says a to the 5th all to the 3rd times b to the 2nd to the 1/2. Why don't you guys pause the video and do example C on your own first, and then we'll check it together. Okay, let's check example C. So the first thing I want to do is simplify all these parentheses that we have going on. So a to the 5th to the 3rd would be the same thing as multiplying those exponents since it's power to power. 5 times 3 would give me a 15. And I can do the same thing on the b squared to the 1/2. 2 times 1/2 would give me 1. I don't have any negative exponents, so I'm good there. And we also know from our last video that because my bases are different, I cannot combine these together. So my first base is an a, my second base is a b. Those are different variables, so I cannot combine this any further. So I can just rewrite it as a to the 15th times b, technically to the first. Okay, let's look at example D. So in example D, we have a to the 3rd to the -1st times b to the -5th to the -3rd. So again, I want to simplify and get rid of these parentheses as much as I possibly can. So I'm going to multiply my exponents since it's power to power. So I multiply those guys. I'll get a to the -3rd then times b to the +15 since I have a negative times a negative. From here, I cannot combine the bases together because they're different bases, but I have to deal with this negative exponent. The way we deal with that negative exponent is to flip it down to the denominator. The b to the 15th will stay in the numerator since that exponent is positive. And we'll end up with b to the 15th over a to the 3rd. So we can kind of see in these last couple examples how we can really put more than one of these properties together in a problem. And as we slowly build up and we learn about all 7 properties of exponents, at the end we'll do a bunch of examples where they've got all or more than one in an example at a time. But we're slowly building up to that as we go through these. Okay, why don't you guys pause the video and do example E on your own first, and then we'll check it together. Okay, let's check example E. So we have x to the 7th to the 3rd. So I know that I can multiply those since I have power to power. So 7 times 3 would give me 21. Then we have times x to the 2nd all to the 4th. Again, I have power times power. So I have x then to the 8th since I can multiply those powers. What makes this one different now is that I actually have the same base. I have both a base of x on each one of these, which means I can use our rule 3 from our last video over here and add their exponents together. So I would get x to the 29th power by adding the 21 plus 8. We had to first deal with the power to the power because remember, in order of operations, I have to deal with anything that is grouping before I deal with multiplication. So that's why we multiplied the exponents first, and then we used our our property number 3 by adding the exponents together because now we're multiplying the same base. Okay, let's look at our property number 5. So the 5th property is kind of similar to that 3rd one, but it's what happens when I divide powers with the same base. So if a is a non-zero number and m and n are rational numbers, then if I have a to the nth power divided by a to the nth, that would be equal to a to the m minus n. So again, this is only working because I have the same base here. So if I have the same base and I'm dividing them, I would subtract the exponents. Hopefully you're kind of believing that because if I scroll back up to our 3rd property, when we had two bases that were the same and we multiplied, we added them. So now if I'm dividing, we're going to end up subtracting them. But let's really go through why that's true. So I have an example down here that says 4 to the 5th over 4 to the 3rd. Well, let's expand out what this means. So 4 to the 5th would be 4 times 4 times 4 times 4 times 4. So I've got 5 4s there multiplied. Then 4 to the 3rd would be 4 times 4 times 4. Now when I'm dividing stuff that are factors, I can cancel these. So one of these 4s can cancel with a 4 down there, a 4 on top can cancel with a 4 on bottom, and a 4 on top can cancel with another 4 on the bottom. And the reasoning behind that is because a number divided by itself, or in this case 4 divided by 4, is going to be equal to 1. What we get left with is then 4 times 4, which we could rewrite as 4 to the 2nd. So if I look back at my original exponents, I had a 5 and a 3, and you'll notice that if I take the top number and I subtract the bottom number, I would get that exponent of 2 then. So the order in which we subtract these does matter, so make sure you're always doing the top number minus the bottom number. And it doesn't matter which one's bigger, it always has to be the top number minus the bottom exponent. Okay, I'm going to fit the whole page on here. So let's look at example 5. So in example 5, it says simplify the following without any negative exponents. So we have x to the 7th over x to the 3rd. I have to make sure my bases are the same. My bases are the same, they're both x's, so I can go ahead and subtract these exponents and get x to the 7 minus 3, which would be equivalent to x to the 4th. Now my exponent is positive, so I'm good to go. I can't simplify any more than that. Let's do the same thing with example B. So in example B, it says b to the 2nd divided by b to the 10th. Again, I have to check and make sure those bases are the same. They're each base b, so we're good to go, and we can subtract these exponents. Remember, it's always the top exponent minus the bottom exponent. So I'll get 2 minus 10, which will give me b to the negative 8 then. Now in this case, I have to simplify this a little bit further so I don't have any negative exponents, but we know how to do that. We can flip this and make this 1 over b to the positive 8th power by using that second property we learned in the last video. Okay, let's look at example C. So example C has quite a few things going on here. So I have x to the negative 2 all to the 5th over x to the 15th. I'll notice that I do have the same base in the numerator and the denominator. But because the numerator has these parentheses, I first have to simplify the numerator and then I can deal with how do I combine them together. So in the numerator, when I have a power to a power, remember we multiply them. So I'll get x to the negative 10th by multiplying the negative 2 and the 5, and then x to the 15th does not change in our denominator. From here, now I can deal with the division. Since I have the same base in the numerator and the denominator, I can go ahead and subtract these and get x to the negative 10 minus 15. So remember, it's always the top number minus the bottom number. Combining that together, I would get x to the negative 25th. Again, have to rewrite it with positive exponents, so this becomes 1 over x to the 25th power. There we go. Okay, let's look at example D. So example D has a little bit more going on it again. So let's take it one part at a time. We have 6 times a to the 4th times b to the 12th over 3 a to the 7th times b to the negative 4th. So I'm going to go ahead and highlight kind of the different sections of this that we have. We have this a base, so I have this a to the 4th and a to the 7th. Then we have these bases with b's, so we have b to the 12th, b to the negative 4th, and then we also technically have 2 coefficients in front. We have the 6 over the 3. Now when we go to combine these, I'm going to break this apart into each one of these pieces. So 6 divided by 3 we can simplify, times a to the 4th over a to the 7th, and then times b to the 12th over b to the negative 4th. And let's look at each one of these on their own. So 6 divided by 3 we are able to reduce down and we get 2. If I have a to the 4th over a to the 7th, I can subtract the exponents because their bases are the same. So we get a to the 4 minus 7. And then I can do the same thing with the b's because their bases are the same. And we get 12 minus a negative 4. Be careful with these with the double negatives because I'm going to end up actually adding them together. To keep simplifying this, the 2, I can't combine with anybody else, so 2 is still there. I have a to the negative 3rd, and then we'll end up with b to the 16th, since this will end up giving me 12 plus 4 when I have the 2 negatives. The last thing to do from here is to deal with that negative exponent. So the 2 and the b both have positive exponents, so those will stay in the numerator, but the a to the negative 3rd will flip down to the denominator and become a to the positive 3. And then we're done with example D. So I think it's helpful to go through and kind of take it piece by piece and see what can I combine together, what can't I combine together. Because as we start to see more and more rules go into play, and we can see in that last example we had a few in there, we want to make sure we're just taking it a step at a time, which is also why it's really important to make sure we're not only showing our work, but that your work is organized so that it can help you see how your thought process is. And on a test, you always want to make sure you're explaining your thought process, and we do that in math by making sure our work is clear and easy to understand. Okay, let's look at example E. So example E looks a little different because I have fractions as exponents, but that's okay. In all of these rules, I've just said that the exponents had to be rational numbers. So they don't always have to be integer values. They can be fractions. All I care about is, are my bases the same? In this example, we do have the same base, so they're both base y. So I can subtract the exponents. So I'll get y to the 3/4 minus 1/2. We've talked about this in past units. If I'm going to add or subtract fractions, I need a common denominator. So my common denominator here would be 4, which means I have to change the 1/2 by multiplying by our fancy number 1, which in this case is going to be 2/2. So I end up getting y to the 3/4 minus 2/4, which would give us y to the 1/4 then. And that exponent is a positive number, so there's nothing else to simplify from there. Let's look at our sixth rule. So what our sixth rule talks about is something that I kind of snuck into a prior problem if you watch the first video of this, but it's what happens when I have a product that is then raised to a power. So in this example, we have two different bases. We have a and b, which are non-zero numbers, and we have our exponent n. So if I have two or more things multiplied, all being raised to that exponent, what I can do is distribute that power to each of those bases from there. And this should seem like, well, that sounds about right. We've done distribution before, and this does work for exponents as well. So if I have multiple things multiplied inside of an exponent, that would be the same thing as taking each one of those pieces being raised to that exponent. So if we raise a product to a power, then we can distribute the power to each factor and simplify. So let's look at our first example here of 6a. So 6a says x times y all to the 10th. So I'm going to distribute this to be x to the 10th times y to the 10th. Now from here, there's nothing else to simplify, so that will be our final answer for part A. In part B, how many pieces do we have inside those parentheses? So how many different parts are being raised to the third power? We actually have 3 different parts being raised to the third power. So we have the 2, the x squared, and the y. So when I distribute this, I have to make sure I distribute it to each piece. And when we have these coefficients, that's where it tends to get a little tricky. But that coefficient is its own base, so we have to make sure that we get 2 to the third, we get x squared to the third, and then we get y to the third. So each one of our individual bases got raised to the third power. From here, we can simplify this a little bit more. So 2 to the third, we know is going to be equal to 8, and then x to the second to the third, we've simplified stuff like this before. This is when I have a power to a power, so I end up multiplying the powers and I get x to the 6th then. And then y to the third is simplified as far as it can be. I have no negative exponents, so that will be our final answer. Okay, why don't you guys pause the video and try example C on your own first. And the first thing I want you to think about is, how many different pieces do I have to raise to the second power when I distribute that exponent? Okay, we have 3 different things that we have to distribute this to. We have the -3, so don't forget about your coefficient. So we have -3 squared. We'll have a to the 4 squared, and we'll also have b to the -8 squared. Now from here, I can simplify each one of these. So -3 squared will give me a +9, because I have a negative times a negative. A to the 4th to the 2nd remember, is our power to our power, so I'll multiply those and I'll get an a to the 8th. Likewise, b to the negative 8 to the 2nd is a power to a power, so I will multiply those and I'll get b to the negative 16th then. The last thing I have to worry about is that negative exponent that I have, so anything that has a positive exponent will stay in the numerator, so our 9 and our a to the 8th will stay in the numerator, and then b to the 16th will get moved down to the denominator and create a positive exponent. Again, the a and the b I can't combine because they are different bases, so that's as far as we can simplify this one. Okay, let's look at our last rule here. So raising a quotient to a power. So this is very similar to our property 6 where I had a product. The difference here is if I have a quotient to a power, then yes, I can go ahead and distribute that to each piece of it. So a divided by b all to the n is the same thing as a to the n over b to the n. So if we raise a quotient to a power, then we can distribute the power to the numerator and denominator and then simplify from there. So let's look at 7a. So I have 7 over x all to the 2nd power. When I distribute this, I'll get 7 to the 2nd power over x to the 2nd power. So I've now distributed my exponent to each part. And now I just want to go ahead and simplify this. 7 squared will give me 49. 49 over x to the 2nd. And we'll be done with part A. Let's look at part B. So how many pieces do I have to distribute that 4th exponent to on part B? We have 3 pieces. We have the x, the w squared, and the y to the 0. So when we distribute this, let me get a little bit more space. So we'll have x to the 4th all over w squared to the 4th. Then we'll have y to the 0 to the 4th. As you'll see, each one of those bases had to be raised to the 4th power. From here, on the numerator, x to the 4th will just stay as x to the 4th. In the denominator, I have powers to powers, so I can multiply those, and I'll get w to the 8th, and then 0 times 4 will still just give me 0. And we're almost done. I don't have any negative exponents, but remember our very first property said that anything to the 0 power is equal to 1, so I can go ahead and simplify this a little bit further by just replacing y to the 0 with a 1, so my final answer would be x to the 4th over w to the 8th then, since y to the 0 power is equal to 1. Okay, why don't you guys pause the video and do example 7c on your own first, and then we will check it together. Okay, let's check 7c. So 7c says a to the 3rd over b. We have 2 different pieces that we have to raise to the negative 5th power. So I have a to the positive 3. No negative. A to the positive 3 to the negative 5th. Over b to the negative 5th. Before I worry about the negative exponents, I want to simplify the numerator as much as I can because I have power to power. We can multiply those and get a to the negative 15th over b to the negative 5th. Now remember, anytime I have a negative exponent, if I flip which part of the fraction it's in, it's going to become a positive exponent. So I'll have to flip-flop both of these since they're both negative exponents, and I'll have b to the positive 5 in the numerator and a to the positive 15 in the denominator. And that will be our final answer then. So in this video, we went through all the rest of the properties of exponents, and we did a couple examples with each. Now in part 3, we'll go through a bunch of examples of how can I see all of these combined together. And that will be